Okay, so I too would like to thank Mark and Mary for inviting me to come over for this talk. Very happy to be here. In fact, this talk is seems like almost a direct continuation of the Professor Merhav's talk, because we have both physics and we have limitations, I guess. Well, it basically is a tutorial. It's not about research much. We are talking about how and if we can reduce size of antennas to fit within systems that people build nowadays. Most of them are very small. Some of them are hand carried. Some of them are wearable. Some of them are carried on vehicles of all sorts of types. And there's an ever-increasing pressure to reduce the antenna. Now, people are telling us very often that they want antennas to be reduced in size. I mean, chips have been reduced, cameras, everything can be reduced by orders of magnitude. Why not antennas? So this is basically my motivation for this talk today. There will be 3 parts to this talk. We decrease in order of ruggedness until we get to lunchtime. So let us try to diffuse a few myths. First of all, people tend to talk about the antenna size as related to either directivity, which is the amount by which you collimate the energy in a certain direction. The larger the aperture, the more collimation you get. And that is an effect on gain, effective area, and so on. And I mean by that you can reduce the beam width by increasing the size of the antenna. Is that always true? Well, the answer is obviously not, because I'm posing this question. And the reason is that if you look at the pattern of, say, a wire antenna, all right, it's the other way around, so. Okay, this is the wire antenna, which has a length of L. There's a current flowing on it. And let's suppose that the current has this kind of shape, or rather distribution along the wire, okay? I call this an antenna in parentheses because very soon we'll discover the antenna is not exactly the physical structure over which the current tends to flow. So if you want to look at the pattern, which is the field radiated in various directions, this is direction theta, relative to the axis of the antenna. So there is a variation in the far field of the field width as a function of theta. We have always 2 factors determining that. This is the Fourier transform factor. What we see here is an integral that transports or transforms the I, this current, this function that I'm showing here, as a function of the position along the antenna, into theta, which is the far field variable. Okay, and it is a Fourier transform because you go from z to k cosine theta. So it's like omega times t in the temporal frequency domain, if you like. And this has all the familiar properties of the Fourier transform. In other words, you increase or you stretch the origin, and you shrink accordingly the transform, and so on. So this has all the properties that we are talking about in myth number 1. But there's always another factor which is very important. There's a sine theta. Now, these 2 factors compete with each other as the size of the antenna changes. When the antenna is quite large, this is the factor that becomes dominant. In which case, the myth is actually not quite a myth. It does hold. And we can shape and change both beam width, directivity, these parameters of the antenna simply by modifying the length. But if we go to very small dimensions of the antenna, this is the factor that begins to dominate. In which case, it doesn't depend at all on the size of the antenna. And that's the point. When the antenna becomes small, nothing much changes in terms of the far field. There's no point in trying to excite the antenna or distribute different variations of current along the antenna as long as it is very small. And by small, I mean more or less this kind of limit. K that appears here is, of course, 2 pi over lambda. Lambda is the wavelength. So we need to distinguish between those small antennas, small compared with the wavelength, and either large or resonant antennas. The main feature, the main important stuff to understand about the difference between these 2 regimes of antennas is what we call the effective area of the antenna. If the antenna is large, and this is always very approximate, this kind of bound, then the effective area normally would be about the size of physical size of the antenna or a little bit smaller than that. However, if the antenna is small, then the aperture size does not depend anymore on the physical length of the antenna, simply because the far field has been determined, it's fixed, there's the sine theta that I was talking about before. So if you change the size of the antenna, the effective aperture, the effective area of the antenna, the effective size of the antenna does not change. This is, in fact, the antenna. And this is why I put a parenthesis normally on the physical structure, on the metallic or dielectric, whatever have you, which is not exactly the antenna. This is what we call the antenna. So if you look at this aperture of the antenna, the effective aperture, we know the directivity and ultimately gain are directly related to it by this famous factor of 4 pi over lambda square. And then the gain and directivity are almost the same, except there is a very important efficiency factor in between them. So for this reason, what happens is that if the antenna becomes very small, this case, then the effective aperture is about the same always for the antenna, no matter what the size is, and then the directivity will not change much. What will change, though, is the gain. The gain is what is ultimately delivered into free space. This is what the antenna and the system on the other side will receive eventually, and this depends heavily upon the efficiency. So what deteriorates is the efficiency, not the directivity when you shrink the antenna. Okay? So again, here the effective aperture depends on the size of the antenna, and here it does not. It's basically the same value all the time, only depending on the wavelength. So for small antennas, the metric is the wavelength. For large antennas, the metric is the size of the antenna. Here's an interesting question now. Is half-wavelength dipole is a large or small antenna? Let's see. This is again the same picture that I shown before, except this time the length of the antenna is lambda, half a wavelength. And this is more or less the pattern. What we see here is that along the z direction there is a null, and perpendicular in the plane, the xy plane, we have a maximum, and we have a beam width between the minus 3 dB points, which is 78 degrees, more or less. This is, you can compute it numerically or in many ways. Let's assume it's true. And now let's compare this beam width to two cases. This is our beam width. We compare it to just the sine theta term, the first one that I was showing you that applies to small antennas. If you only take the sine theta term, then the beam width would be 90 degrees. This is the beam width of what we call an elementary dipole, of a very small element of current. If, on the other hand, you look just at the second term here, the Fourier transform term, then there's a formula that will lead you to some kind of ridiculous number, which is 134 degrees. Obviously, we are much closer to that. So the antenna, which is already half a wavelength, which is resonant, still displays more or less the characteristics of a very small antenna, rather than a large antenna. There's not much point in playing around with the current distribution of this antenna. If it's like half a cosine, like I'm showing here, whether it would be any other kind of distribution, we'll get more or less the same, the same performance in the far field. So the answer is, it is closer to a small antenna. Here's another question. Okay, we'll be in the other question very soon. And now let's see what happens. Here's the next question. Yeah. So we just said that for a half wavelength antenna, it's basically small. If we shrink it, nothing much happens. So why not shrink it? Why take such a long real estate? If you are looking at very low frequency, sometimes these whip antennas, which are dipoles, are very long. Let's shrink the antenna. What will happen then? The issue is totally different now. It's not the directivity, it's not the far field, it's not the beam width, it is the impedance and the efficiency, this eta that I was showing you before. Here's a graph that shows you what the real part and the imaginary part of the impedance of a wire antenna look like as the frequency grows in this direction. If the antenna is resonant, which is lambda over 2, resonant meaning that the reactance or the imaginary part vanishes here, then we have an impedance which is the order of 70 something ohms. And this is how the antenna operates. If we shrink the antenna or alternatively bring down the frequency, it's about the same thing. What happens is that the real part will go to zero, more or less, roughly by lambda square, or by the square of the frequency will decrease to zero, whereas the reactance will become very capacitive. In fact, when you take a very small antenna, it almost looks like a perfect capacitor, like a pure capacitor. It doesn't radiate, it simply stores the electrical energy. I'm now blowing up this circle here to show again the same effect that I was talking about. This is the point here. So this is a half a wavelength dipole. And look what happens when we make it smaller, okay? So there's no point in trying to build something which is very close to the origin, not because of the far field again, but because of the impedance. What happens if we are trying nonetheless to do that? Here's again our half wavelength dipole, and let's say we're trying to build a small antenna. Okay? Here's the challenge. Let's build a small antenna. Well, the current has to be 0 on both edges, right? Because it is flowing in the z direction, it has to be 0. So it's both 0 here and there. In between these two edges, there is no space for the current to be large, and for this reason the antenna is inefficient. It doesn't really radiate. In order to radiate, you need some kind of power, some kind of energy in the antenna so it can radiate outside. There is no current here. Basically, it's like an open circuit, or I should say a capacitor. It's not an open circuit. It's an open circuit for DC. It's a capacitor. Okay? And this is simply because we have something that, in fact, when omega does go to 0, it does become an open circuit. But people will come and say, why won't you just impedance match the antenna? If we impedance match the antenna, it will radiate. Let's add a matching circuit now to this small antenna and try to match it. So this is again our reference. And what happens now is that if you are able to match the antenna somehow, in fact, what you're doing is you're increasing the current a lot over this very small segment of wire. But what happens then? If you do that, we have seen that the radiation resistance, was the red line that was going to 0, is becoming very small. And no matter how small the losses are, they will become dominant. So the power that you are trying to feed into the antenna will go more or less into losses in the antenna, no matter how small the loss mechanism is. So this is why it's so difficult to excite a small antenna. You will get a very nice VSWR at one frequency or maybe a very narrow bandwidth, but it will not radiate very efficiently. Here's the point. You can see this happening all over the place, over and over again. We have a microstrip antenna, which is a rectangular patch, which is etched on top of a kind of substrate fed by this microstrip line. As you take the thickness of the substrate and decrease it, you can see that the efficiency, this axis is the efficiency, okay, goes down between the lines. I'm just showing you several lines that are going down. So we have competing issues. We have the efficiency, the form factor, which is the size, and the bandwidth, all competing with each other, and there is really no good way of doing that. If we try to bring two antennas close together, if it's a resonant or larger antenna, you can actually take the physical structure, which is now a purple here, and bring them closer together. If you take two antennas in parentheses and bring them close together, the effective areas will overlap, and actually they are connecting them almost physically. It's like taking two wires and just putting them together. If you connect them, you cannot excite them independently. If you just take them a little bit apart like so, you can still not excite them independently. You have to take the distance between them much larger, so the effective areas are not ones that would overlap. Here's a demonstration of why it is true. What we see here, we see the directivity of an array. Array is made of a bunch of small antennas. Here we have an array which is 5 by 5. It's planar. There's 5 elements in each axis. And we see the directivity. If the elements were uncorrelated totally, then the directivity would simply be the summation of all directivities of the individual elements. And this happens only if you take the distance between the elements to be fairly large. This more or less levels out and you get something like so. But if you get them close together, you can see directivity drops to 0 because you cannot add the directivities together. So you cannot excite them. Coupling is inherent. That's what I'm trying to say here. Some people think that coupling between elements in an array is a parasitic factor. Let's work coupling. Let's reduce coupling. Let's try to do something about the coupling. Well, since the effective area is very basic physical phenomenon, there's no way you can get rid of coupling. It's built into the electromagnetic theory. You will never be able to get rid of it. You will never get to reduce it. And there's no way you can bring elements very close together. This should tell you what happens if you're trying to put on the same handset lots of antennas for all the applications that I've shown in the first slide. It's just not doable. Anyway, but suppose we are trying to miniaturize antennas. There are tactics to do that, and what I'm going to show at the end, the bottom line of all this presentation is going to be that there is a limit to how much you can miniaturize antennas. Let's start with invading property. This is your average monopole antenna on your brand new shining BMW. Okay, actually it's not a BMW. They have a patent of making the antennas smaller again, or blade antennas that you can put on aircraft and so on. I just happen to have another monopole antenna here, okay, on a ground plane. The reason it's conical is because it's supposed to be very wideband, operates all the way from 1 gigahertz to about more than 10 gigahertz and so on. Is it a small antenna? It's only a quarter wavelength. The answer is no. It's not smaller, it's actually larger because you invade this area, you excite the ground plane with currents, and they are an inherent part of the antenna. If you chop off the ground plane, there's no antenna, it will not radiate, it's just a passive load of some sort. Okay, so it's a quarter wave monopole is a larger antenna than the half wave dipole. That bad. Here's another example from the literature, fairly recent, I should say, about how you invade the PCB. This is what people call the antenna in a handset. Okay, but in fact the antenna is the entire handset. You invade the PCB, and in fact not only that, you add something down here which they call the wave traps. But this was quite early on. Today we would call it probably metamaterials, okay? Because it's sort of a small periodic structure that goes around it, without going into the details. So the entire handset is the antenna. What you see here is first of all that my pointer is lost, which is no problem. It is a problem for the next guy, but I have this. So what you see here is you see basically a dipole. This is one arm of the dipole, and the PCB is the second arm, and then you feed them in between. Okay, anyway. People are tempted to try and shrink the antenna by coiling it or meandering it and so on. And it does make sense. People do that. What you see here is, again, you're trying to build a very small monopole over the ground plane. And if you build it like so, it will never work. But what you're trying to do is you take a longer wire and bend it so the overall length will become closer to about... No, all right. No, I'm fine.
You have an antenna.
Here. Antenna, thank you. I always have this. Okay, thank you. Anyway, so you try to bend it like so. And what it means is that you are adding all kind of... If in another way of looking at it, you're adding all kind of lumped elements that are basically reducing this, loading the antenna and helping to reduce the size. So it's all the same, meandering, adding elements. It's a different way of looking at the same thing, and it can work. This antenna was built by a student of mine a long time ago. And what you see is you see the meanders and lots of other meanders, and you see the feeding on the bottom side of the print, and there's another meander. And yeah, you could shrink it a little bit. But how much? I don't know, 20% or so. These are other examples from the literature. Ohio State University. This is one way of meandering a dipole. You can still see the dipole. There's the dipole. This is one arm. This is the other arm. You start meandering one, and then you keep changing it, and you get all kinds of return losses versus frequency. And then you can also get the two arms to overlap in a way. If you see here, this arm goes in this direction and so on, and then add more and more meanders. But the point is that if you do that, you have to be very careful, because you cannot really expect the current to keep flowing along the meanders the same way it would flow along a long straight line. What you need to make sure is that if you're looking at the current in one meander, then you have to go around, and the current in the next meander should go in the same direction. Okay? And if you have another one, still in the same direction. So it is an art. People try to get a hold of it. You can shrink the antenna, right? By how much? Not a lot. And you can do it even in 3 dimensions. That's another work from Ohio State. You can see that here what they do is they meander in the perpendicular direction. This is a cross dipole which is supposed to produce many different polarizations, if you like. You can take the what we call the PIFA, planar inverted F antenna that you have on your handset. It's not very clear here. I apologize for that. And you also can meander it a little bit. That's another good example of meandering. Okay, and this is the bottom side where you feed it on one side, and this is the ground plane for the rest of the antenna, done by a company called E-Antenna for Ericsson. More interesting idea. I would like to call this the twister, tornado antenna, right? You both twist it in one, and then you add in one dimension, and then you add more coils, like so, and you can change it. And this is the top view of the same, looking from, say, the top down. Okay, and you can see that there are more coils here and there. And again, you align the current right, and you can reduce the antenna. By how much? Not a lot. Again, not a lot. This is very complex to build, right? This was antenna, again, done by a long time ago by one of my students. He works for Motorola. Shachar Aviv, his name. You see here another example of meandering. This is a path for the low frequency, and there is also another path on the other side for the high frequency. But the ground plane or the PCB of this set is an integral part of the antenna also. So what you have here is a combination of meandering and invasion of the ground plane. Fractal antennas. A few years ago, it received a lot of attention. This is the famous Koch fractal. It's basically another way of meandering. Here we can see space filling curves that go from here, through here, through here, through here, all the way up to here. It's called the Hilbert fractal antennas because of the Hilbert space filling procedure. And this is a patch antenna that again evolves into this direction and so on. But in terms of reducing size, it's the same order of magnitude like I was talking before. This again antennas from Ohio State. They call it the inverted hat antenna. I call it the shrine of the book inverted, right? Isn't it? Am I right? Okay. And interestingly enough, they got the antenna to evolve from here to here to here to here. And this realization is what, by strange coincidence, we also came up with. And this is our second example, which is can hardly be seen here, but perhaps here. See? You can see a little bit here, hopefully. Okay. We have been able to shrink this monopole into this size, squashing it by altering the contour in a similar way to what was done here, except we did it in a very brute force way by using genetic algorithms. So this is the antenna that you see right here, and then further on we developed it into a dipole antenna, and then to cross dipole, and then it was packaged like so and tested in our anechoic chamber next door. That was done for the Short Range Consortium here in Israel, which is about to finish in a couple of months. Okay, reduce the wave speed, slow down the wave. We can use lots of materials for that. There's also the option of using metamaterials. And basically the idea is the epsilon becomes larger, the wave speed becomes smaller, and you can reduce the antenna. By how much? Just about the same order of magnitude. Here's a work by the group of Zulkowski from University of Arizona. Metamaterial is a very, how should I put it, it becomes very popular these days to use metamaterials for different purposes. And what they did, they took your average monopole and backed it by this metamaterial, which has negative mu, negative epsilon properties. And you can see photographs of this. And they were able to reduce the size of the monopole quite substantially. But this is a part of the antenna. If we talked about the effective aperture before, this definitely fits within the effective aperture, so the total size is not that much of, it's not been reduced a lot, and also the bandwidth, which is not shown here, is very minuscule, very small. And this is fairly recent. Then we can load with the lumped elements. This is an example of a slot with a stub added to it, and on the stub you have loading with the changing capacitors realized by MEMS. So you can control a little bit the antenna. This is also a slot, as you can see here. This is the microstrip line that feeds the slot, and this is the transformer and the stub to match the feeding point. But then the slot goes and curves around. Again, it sort of meanders around and around. You could call this an inductor, if you like. So you were able to reduce the length of the slot simply by letting the field go around and around like so. By how much? You know the answer. Right. There is a design example that I'm going to skip that we did here that led to development of this antenna here, which is, again, we see a structure here and then the entire PCB. It was supposed to mimic a cell phone antenna for a senior project. This is what normally appears in most of the telephones that you are holding right now. It's called the planar inverted F antenna. It's fed here. It's short-circuited here. It's based on the reduction of a patch antenna into a half of the physical size by realizing that the field along the black line here is 0, and therefore you can short-circuit it here and eliminate this area there, if you like. But again, the effective area stays about the same. You have not done much of the effective area, and you put it on top of your PCB, and the whole thing together acts like an antenna. Okay, so the short circuit here is the black line. The feeding point here is this feeding point pushed inside a little bit, and this is how this evolved into this, and this comes down to this. So now what you do is you do a lot of stuff that I will skip to get eventually what I'm holding here. This is the entire structure. It has meandering. It has two paths for the two frequencies at which it operates. It's a long path for the low frequency. It's a shorter path for the high frequency. You get the two frequencies. And you have been able to, shrink this part a little bit. But look at all this. Okay? That's it. In fact, what I skipped now was part of the design process was an effort to excite the PCB as much as possible, or to rather enhance the coupling between the PIFA and the rest of it. Okay, and finally, there are fundamental bounds that have been developed over many years. What are the key issues? The key issues is this. Again, here is the directivity I was talking about. The E is the eta. This is the efficiency. This is the reflection loss here. And finally, this is what you can realize as a gain. The key issue here is this. The directivity, you cannot, when you shrink the antenna again, like I was pointing out, cannot be shrunk under a certain limit. Very difficult to match, because with small antennas, again, the real part goes to 0, the imaginary part goes to minus infinity. And then there's the issue of the efficiency. Efficiency is the radiation loss divided by the total radiation, the radiation loss divided by the input resistance, which is made of both of radiation and loss resistances. So you want to reduce this, you want to reduce this. These are the key issues. The parameter that takes care of just about everything is the quality factor, the Q. there are many definitions. And what we can see is that, again, if you go down with frequency, which is equivalent to reducing the size of the antenna, Q goes up very high. That means that you have, in the near vicinity of the antenna, a lot of reactive energy stored relative to the power that's been delivered to radiation. Okay? Simply because, like if it's a wire antenna, it's simply a capacitor. So it stores energy but doesn't radiate it. This is the effect of the high Q close to the origin. Now, people are trying to to reduce the Q for small antennas. How much can you reduce the Q? All right, so this was the topic of research that's been going on up until these days, up until very recently. As you can see here, started from the 40s, probably before that. This is a very tough problem. Back in the 40s, it was already a tough problem. Okay? And people have been re-evaluating and redoing it over and over again through the years. In fact, the last paper that came out in October 2009, that I'm quoting here, is a modification of the Q formula from 48. There is the original Q and there's a delta Q that I have added recently. Okay? Probably one of the most famous papers is the one by, where am I? By McLean. And what basically they do is this. We want to reduce the Q. What's the minimal Q that we can get? This is the general definition of the Q factor. This is the stored energy. Should be either electric or magnetic. You take the maximum. This is the frequency where you operate. And this is the radiated power. Now, people look at a circle that bounds the antenna. That's already a problem, but it's rather easy to solve. And what they do is they compute all these quantities here and there outside the sphere, assuming that there is no power, or rather no reactive energy stored within the sphere. I'm not going into these equations. I'm not trying to point out that if you look very close to the antenna, you have terms that look like so. R squared, R cubed. Okay? And that means that when you get close to the antenna, the field changes very rapidly towards the origin of the antenna. So this is why you get a lot of stored energy very close to the antenna. But with these models, they look outside the sphere, and then they compute the stored electric energy and magnetic energy. That's all I'm trying to say here from these expressions. These expressions relate to spherical harmonics expansion of the field, and this is the lowest order, TM01, which also coincides with the field of what we call elementary dipole. Each spherical harmonics has a dipole moment associated with it as a source, but that's beside the point. So, having worked a lot about this, I'm skipping all the details. What we have here is, again, I'm repeating here the definition of the Q, but what you see here is this. A is the radius of the sphere I was talking about. K is the propagation constant, 2 pi over lambda, and there are two terms. If A is very large, okay, then this term is negligible, and what you get is this term, which is, well, if you increase the size, which is A, Q drops, which is fine. But once A becomes very small, again, this term begins to dominate because of all these higher orders of the variation versus R that I showed in the formulas before. And you get very high numbers when Ka becomes very small. And now people are trying to modify and adapt this limit to reality, and then when you realize antennas, people are trying to get as close as possible to the limit. This is a comparison between computations of Qs versus the radius of this field that I was talking about. When the antenna becomes very small, they all converge to something very similar. So McLean was the work I was just quoting, but there are, of course, other works, and they differ in the region where the issue is not that much, but they become very close together for very small antennas here, and the Q, like I said, goes very high. And I'm sure that in the future we'll see more and more publications about the same thing, because the actual limit is quite fuzzy, still fuzzy, and people are trying to get to it. And as a conclusion to everything I was just saying is that we have been trying to shrink antennas with all the limitations I was talking about. This antenna here that's on the table has been shrunk about by this amount from 58 something to 32 millimeters with the same, pretty much the same performance, give or take. But at least up to this point, we have not been able to shrink it much more. And I think that this is more or less the ballpark of what you can do. We have seen that miniaturization is limited by all the physical bounds I was talking about, that efficiency drops and also bandwidth drops very, very fast with the size of the antenna. And all these techniques for shrinking or miniaturizing antenna are limited. I'm trying to make it a bit extreme in presentation, but that's probably the way to try and convey the message. So people are trying to do wizardry. I have been approached by people who've been asking me, so what about all this? Can you do some, still, we need something very small. Can you do some hocus pocus? Well, the answer is no. Beginning of next month, there is an entire conference devoted to miniaturization of antennas. I'm going there with moderate hopes. Thank you very much. This is amazing.
Yeah. One particular thing that become interesting in wireless communication is MIMO.
Yeah.
Not only want to, we want to put many antennas and generate different signals in each of them.
Yeah.
Not only to make the antennas small, but also to make them close together. So, I don't know, what are the chances there?
Well, since MIMO was one of the issues, wasn't it? Let's see. We were talking about MIMO. I was trying to mention that too at the beginning.
No, MIMO is different than just an array.
I know, because, yeah, what I'm saying is that everything I was saying in this presentation was about working about the same frequency range. There are other factors. Of course, if you work at different frequencies, okay, that's fine. But if you want to accumulate, say, I'm not sure about whether it's MIMO or not, but for diversity, we want to accumulate signals at the same frequency from different directions, different polarizations, and so on, then everything applies. But if it's different frequencies, then...
same frequency, but different signals in each antenna. That's the MIMO.
Well, then the problem is there. I believe the problem is definitely there. Okay, this is where I don't know. This is the case I was trying to make when I showed you, where was it? When I showed you that it's very difficult to bring two small antennas close together. So the problem is definitely there. If you want to bring the antenna any closer than lambda over, say, 3 or so, they will interact. So this will have an effect on the correlation between signals. We're looking at a bit correlation stuff also to figure out how that works.
The lambda over 2 or something, this is the thumb rule it applies.
Well, you can, like I said, since everything is so fuzzy and people have been trying to find bounds because it's so fuzzy, and you can see by the amount of work and the limited success, we don't have very strict bounds, then I would just shoot at the lambda over 3. This is the baseline that most people are talking about nowadays, and that's about it. Now, with the polarization, of course, you can get much closer. Yeah.
What is the effect of the human hand holding the phone?
Oh my goodness. Oh, you want me to answer that? The human hand, and especially the human brain, are major factors in reducing the efficiency of the antenna. Okay, you are holding the phone like so, right? This is my 0 generation phone, works perfectly. And what happens is about half of the power goes into your brain. Half, just about, okay? So the eta or the E that I was showing, once you add that to once you add the tissue to the picture, drops very substantially. So the Q drops, but it doesn't go to radiation; it goes to losses. Okay. There's no. By the way, I didn't mention the simple idea of just adding losses. People have been designing antenna with larger losses. There is a famous something called the Kanda dipole, which had conductance lined along the wire. There have been attempts and just introducing losses, but that's not the issue I'm talking about. לא חוכמה.
Also detunes the
Yeah,
antenna.
Yeah, sorry?
Human tissue also detunes the antenna.
It was what it does? Detunes, sure. It tunes the antenna, of course, because
But also detunes.
your entire physics becomes part of the radiating structure, for better or worse. It, of course, including detuning and lots of everything. Yeah.
Does it work with the loop antennas with ferrites inside?
Loops are the analog or the dual of the wires. You can look at loops like magnetic currents. I was showing an electric current. If you just replace everything by magnetic current, then loop has about the same performance, the same characteristics. With one, I would reserve myself with one reservation. Since you are feeding it differently, the impedance behavior close to the origin, close to the zero frequency, it's even worse. It's much faster, goes much faster to zero than for a dipole. That's because of the feeding structure.
What about ferrites? You can add
Ferrites? People are using ferrites, yeah. The list of materials that I showed before also included ferrites. So ferrites are a good idea. They are just non-reciprocal and they are heavy and things like that, but people use ferrites, yeah. As part of the idea is either you increase the epsilon or increase the mu. Ferrites increase the mu, but not in an isotropic way. Okay. There was another question. All right.
Loudspeakers, it seems that the technology was able to make them so small. In recent years, I was buying a stereo system and the loudspeakers. Sound wave is totally different, I guess.
You talk about the Bose speakers? The Bose speakers have inside them, they have this coiling stuff, same as I was showing here.
They're,
Yeah.
It's smaller.
I mean, instead of something like that, it became.
Listen, it's a different regime of wavelengths. I'm not exactly sure what was reduced to what there, but I never looked into it. But basically, the idea of coiling and meandering was about the same. I also own these little things, and they sound great. Yeah, I have no interest in Bose or anything.
But maybe something more serious.
Yeah.
I know that sometimes when the antenna somebody stands or there is something near the antenna, it can influence on the positive side. I mean, if you knew that the antenna is near some metal body, for sure at some range near it, would that significantly change the picture?
Well, it's like you take a dipole, half wavelength dipole, and you put it next to a conducting screen, which is a ground plane, at a quarter wavelength away, and it will enhance the radiation in the other direction. True. True. It will enhance the activity, but the whole structure is about the same. It's about, well, what happens is that you excite the ground plane, so you enlarge the effective area. Again, there's a ground plane is being excited, there's current flowing it, so larger effective area, and it can happen, it happens.
So how much can you gain? Again,
Well, at the peak, you can gain 6 dBs theoretically, tops. Yeah. For the gain. Yeah.
You say that when you take a quarter lambda antenna and put it over the ground,
Yeah.
you get a long antenna.
A larger antenna, yeah.
Yeah. When the half wavelength is not a long antenna, but I knew that a monopole over ground is exactly half wavelength antenna. But
Well, this is textbook material. Let me try to explain it very briefly. Here's the dipole, and this is the radiation pattern, right? More or less. Here's the monopole, and this is the radiation pattern. See the difference? There's nothing here. So you have a narrower beam here. It's the same. The field distribution is the same, but it's chopped in half. The beam is narrower. Obviously, the aperture is larger. Yeah, it's a textbook. It's actually an exam problem. Yeah,
What about superconductor?
that's okay. What?
You said you thought that
Yeah.
Right? So suppose that you can use superconductor material.
Ah.
Could you shrink the antenna then?
Yeah, people do that. People are trying to do that. The whole issue of shrinking antennas, getting close together, and trying to overcome the inherent loss as application, of course, to arrays, because for the reason I showed, and to something abominable, which is called the superdirective arrays. People are trying to do that. There's a lot of literature about it. I don't know how successful it is, but people do that. Are trying to do that. I haven't seen much results, much anything produced out of it yet. It could work. I don't know. Yeah.
Isn't the theoretical limit because you're picking up an energy from the space around you? So the energy you pick up is connected to your physical area. You cannot pick up an energy from far distance.
So?
At the end, your physical area, as small as it is, limits you. You cannot get high directivity from very small antenna. Because the radiation radiates only the area that you are in.
You're talking about receiving antenna?
Yeah.
Yeah, when you receive antenna, there's effective aperture. If you mention antenna, which is fixed in terms of wavelengths, not in terms of the physical size of the antenna. Well, there are lots of antennas that have.
The physical size of the antenna, because.
What is the physical size of the antenna? The material size? Okay, we can talk about it later.
Take it offline because there's
The physical size is where the field is.
Yeah.
Okay.
we want to start on time.